If you recall from your collection lectures where we talked about the sorted array based collections, the implementation for that one is roughly the same as the other one. The only difference is now we're using lists. We're going to be employing comparator as well as a comparable interfaces is in this implementations here. And the other thing about the list implementation is both add and set operations, they're not supported for a reason. And let's just move on to the actual UML for the sorted list implementations. This is what it looks like. On the very bottom, you see our list implementation. This is the sorted one. This one implements the list interface, as well as implementing both comparable as well as the comparator interfaces. We can use either comparable or comparator to make comparisons of the objects sitting inside this list. We're just using both implementations, just like before, one and two different methods to illustrate the effect of having a natural order comparisons. Everything else looks exactly the same as the collection. Let's go back to the initial page where we talked about the differences. There's a reason for why both add and set operations are not supported. This is because it does not make any sense if something is sorted already that you would want to force a specific element be dropped in a certain locations. This is not good, so is set. The difference between add and set is set returns the elements removed. Add does not do anything, simply just force an insertions there. Having this specific force insertion is not a good idea on a sorted array because we need to invoke what's called find or search to find the appropriate location for any given element based on their natural order in this case before the insertion happens. Having a force set on a given index is not allowed. This is the reason why we use unsupported operation exception to prevent this from happening. Whoever does the invocations would have the responsibility of catching this unsupported operation exception. Let's look at the specific. The anomalies for this one looks just like your collection interface. This is the list. Now you have this comparator as well as the comparable implementation. This comparator is getting passed in this custom constructor. You have another constructor, the default constructor that creates anonymous comparator class. And comparator implements this abstract method called compare that does the comparisons inside of it. So this allows you to compare the two elements. This element T, which is passed in here, has a comparable implemented. And this is actually done downstairs. So you can see that using a comparable, by casting it to comparable, this element can do a compare to. Because now this is a sorted array base, the implementation of binary sort is actually enabled here. This binary search, not sort, is available as part of this, finding the middle ground, checking to see if the target is on the left or right hemisphere. If found, then you recurse into it. So this recursion find is part of your find. Your find sets the initialization. As long as this is not empty, then you recurse into this. This is O of log n base 2. This is very efficient algorithms for you to find the elements in a specific spot. Recall that find as well as your remove both invokes find. Find is very important. You are able to optimize it. The remaining operations for remove and add becomes very, very efficient. Recall that if you just add an element into a certain spot, you have to shift all of the other elements out, right? Forward by 1. If you're trying to remove something, then you have to shift all of the elements after it up until n element, number elements minus 2, forward by 1. It's the logic that is similar to collection. And if you move down to the very bottom, you'll see the comparable implementation. This is the iterator part. Let's go back to our lecture. The Java comparators that we illustrated before defines the two abstract method. The only thing that we need to really worry about is the compare methods to do a comparison. You can also do the equals, but equals gives you a Boolean. We're interested in integer comparisons. This gives us a integer that is either zero, greater than zero, or less than zero, positive or negative. This is the comparator interface that we'll be using. This is an example of the famous person. If you use the comparator and interface, you have to create a concrete class. This is the domain class called famous person. Because the compare is an abstract method, you have to implement it using the comparator, passing in two objects that you're trying to compare, create a integer comparisons algorithm, subtracting each other's year of birth and get the integers out. This is one example of how you can use the Java comparator. As we saw earlier, that there are two constructors, right? One is the one that creates this comp, the instant variables that we want to create. This comp is basically implementing the specific algorithms that allows you to compare the two objects. And the other one is if the comparator is already available, you can pass it in and simply just set it. If you move down to the other portion of the code, you'll see the use of compare. This compare is being found where every time you're trying to compare the object. So this is no longer integer against integer. This is comparisons of object one against the other objects. The comparator being passed in, you will get an integer outcome. Or you can make use of your own compare method as part of the comparator to achieve this outcome. The element itself must have a comparable interface. This is the constructors that we were just talking about. We're going to scroll down the bottom and you can see this is our sorted array-based list implementation. So we encourage you just to run this through in your ADE and make sure that you exercise some of the methods here to understand fully.